The next topic is modeling gas turbine power plants. In the previous topic about internal combustion engine, we only have one component, which is the combustion chamber, and this combustion chamber is surrounded by the cylinder wall and piston, and all process compressing the cycle is conducted under this one component. In this gas turbine power, we will have several interconnected components. Each of these components will do a certain function in the cycle. So gas turbine power plants may operate on either an open or closed basis. On the left side here, we have a schematic of an open gas turbine power. So the working fluid is here is air. Air is drawn into the system by the compressor, and then the compressor get the power from the turbine through this interconnected shaft, and then at the exit of the compressor, the working fluid pressure increases as well as the temperature, and then it's enter the combustion chamber, and the fuel is introduced into the combustion chamber, and there will be a combustion process inside this chamber, and at the end of the process the pressure and temperature increase, and then this high pressure temperature working fluid is flown into the turbine, and then there will be an expansion process. So the turbine produce work. Some of this work will be used to drive the compressor. The rest of the work will be used for other purposes. And then the working fluid exit the turbine as a product of the combustion here, and then it will go to the surrounding. So this is a kind of an open system. As you can see in this open system, we don't have thermodynamic cycle process here. And then on the right side, this is a closed gas turbine power system. So we have, let's say here is operating point number 1. The working fluid is compressed when it's flow through the compressor going to state number 2. So P2, T2 are higher than P1 and T1, and then this working fluid then flows through the heat exchanger, through the heat exchanger. So what is introduced into this heat exchanger is a Q-in, not the fuel. So there will be a heat transfer from external source to the heat exchanger to increase the pressure and temperature of the working fluid. And then let's say here is operating point number 3. Then this working fluid will flow to the turbine, and then there will be expansion process. Same thing as left side. So some of the work will be used to drive the compressor, and then the rest, which is the network, will be used for other purposes. And in this closed system, let's say this point 4, this working fluid is recirculated back to state number 1 here by a heat exchanger. So inside this heat exchanger, there will be heat transfer disposal to the surrounding, which is Q out. And similar to the analysis of internal combustion engine, we will use air standard analysis. So in this case, we'll assume that the working fluid is pure air, so 100% air, so we can ignore the impact of the fuel properties as well as the impact of the combustion product. So in the internal combustion engine, we have Otto cycle as the basis for the gasoline cycle, and then we also have a diesel cycle as the basis for the diesel cycle. And then if you look back for the vapor power cycle, we have Rankine cycle as the basis of the vapor power cycle. So for the gas turbine power system, we have a Brayton cycle as the reference. So in this Brayton cycle, it is assumed that we have operating point number 1 here entering the compressor, and then at point 2 we have a higher pressure and temperature, and then heat transfer is introduced into the heat exchanger, and at point 3 we have a further increase of the temperature. Pressure is assumed the same between point 2 and point 3, and then the turbine will do an expansion process. Some of the work will be used to drive the compressor, the rest will be used for other purposes. And then at the exit of the turbine, it is state number 4, and in this Brayton cycle, it is assumed that the working fluid at state number 4 here will mix with the mixture in the surrounding, which is actually air consisting of oxygen and nitrogen. And then there will be a heat transfer as well from the working fluid at the state 4 here with the mixture inside the surrounding, that will make the state of 4 here back again to the state number 1. Okay, so this is the idea behind this Brayton cycle. Okay, so once again we have point number 1 and then point number 2 after the working fluid flows through the compressor, and there will be a Q in here, not the fuel, and then point 3 here has the highest temperature, and then the turbine will conduct expansion process. Okay, and then point number 4 here, it will go back to the surrounding. So let's see how we evaluate the process inside this gas turbine power system. So we can do the same method as we did for vapor power system. So in this case, we can assume that there is no impact of the kinetic energy and potential energy change, and then by applying mass and energy conservation on each component of the gas turbine system, we can get several equations that can be used to estimate the performance of the system. So the first conservation is applied to the turbine component. So we will get equation 9.15. So the turbine work per unit of mass is the enthalpy difference between the inlet and the exit. So we try to have a positive number here, so just to avoid the confusion. And then in the compressor, you can see in here that the compressor work per unit of mass flowing is H2 minus H1. So this is the enthalpy at the exit of the compressor minus the enthalpy at the inlet of the compressor, and this is also positive. This is positive, this is positive. Okay, and then the heat added to the cycle per unit of mass, equation 9.17, this is H3 minus H2. So this is the enthalpy at the exit of the heat exchanger or at the entrance of the turbine minus the enthalpy at the entrance of the heat exchanger. And then the heat rejected per unit of mass, equation 9.18, Q dot out over M equals to H4 minus H1. So this is also positive because H4 is higher than H1. And then thermal efficiency of the cycle is the net work over the Q in. So in this case, all parameter here is per unit of mass. So W T dot over M dot minus WC dot over M dot, and then in the denominator here we have Q in dot over M dot. So equation 9.19. And then the back work ratio for the cycle is the ratio of the compressor work over the turbine work. And you will see later on in the example that the back work ratio for a gas power system, gas turbine power system, is much higher than the back work ratio for a Rankine cycle. So because the working fluid is air, we will use either table A22 SI unit base or A22E for British unit base. This is the PV and TS diagram for an ideal air standard Brayton cycle. The area on this diagram, so on the TS and PV diagram, can be interpreted as heat and work respectively. So on the TS diagram, it can be represented as heat, and then on the PV diagram, it can be interpreted as a work. And these parameters are per unit of mass flowing. Let's take a look on this TS diagram. The area surrounded by point 2 and then point 3, so point 2, point 3, and then A, and then B, back again to 2, represent the heat added per unit of mass. And then the area surrounded by point 1 and then 4, A, B, back into 1, represent the heat rejected per unit of mass, and the difference, which is the net heat, equal to the net work. Okay, let me put a pattern here. So this is the net heat, which is also the net work of the system. And then on the PV diagram, so on the PV diagram, the area surrounded by point 1 and then 2, and then A, B, back again to 1, represent the compressor work input per unit of mass flowing. Okay, once again, so it is to the left of the process line. Don't confuse with this one. And then the area surrounded by point 3, 4, BA3 is the turbine work output per unit of mass flowing, and the difference, which is the network, is the area, okay, surrounded by the process line. Like in the Rankine cycle, our task is either to maximize this network or to increase the system efficiency. Okay, for the analysis, we can use equation 9.21. So this is the correlation between the pressure ratio and the PR ratio, and then between point 2 and point 1. So this is inside the compressor, this one. Or equation 9.22. This is the process inside the turbine. Okay. So usually point 1 state is given, so pressure, temperature is given, and then the pressure ratio is given, so P2 over P1 is given. Then you can get PR2, and then you use table A22 or A22E to get enthalpy at point 2. And then the state at point 3 is also usually given, temperature is given, and then P3 equal to P2. And then if the temperature is given, you should be able to get the enthalpy. Then from equation 9.22, you will be able to get PR4, and then going back again to table A22 or A22E, you will be able to get H4 by doing an interpolation. So if you look at on this TS diagram for an ideal Brayton cycle, we have two isentropic process. So one is inside the compressor, second one is inside the turbine, and two constant pressure process. So 2 to 3 is within the heat exchanger, and then 4 to 1 is also within an heat exchanger. This is an idealized or an assumed heat exchanger to bring the working fluid back from state 4 to state 1, so that we have a cycle. Okay, let's have a look at this example. In the book, this is example 9.4. Air enters the compressor of an ideal air standard Brayton cycle. So ideal Brayton cycle. So we have two isentropic processes and two constant processes. So at the entrance of the compressor, the state is given there. So pressure is 100 kilopascal or 1 bar. Temperature is 300 Kelvin with a volumetric flow rate of 5 cubic meter per second. The compressor pressure ratio, so this is P2 over P1, is 10. The turbine inlet temperature is 1400 Kelvin. Determine the thermal efficiency of the cycle, and then the back work ratio, and the last question is the net power developed in kilowatt. Okay, let's see the solution of this example. On the left side is the schematic of the system. We have a compressor, and then point 1 state is given there, 1 bar, 300 Kelvin, and then point 2, we don't have the pressure and temperature, but P2 is 10 times P1, and then at point 3, temperature is given, 1400 Kelvin, and then the turbine will do an expansion process. Some of the work will be used to drive the compressor, the rest will be in the network that can be used for other purposes. And then the S diagram is on the right side, we have state 1 and then isentropic process, so S2 equal to S1, and then from 2 to 3 is a constant pressure process, P3 equal to P2, and then 3 to 4 is isentropic process, S3 equal to S4. And this is the engineering model. So I need to mention to you that it is very important to include this engineering model or assumption when you are solving the problem in thermodynamic 2, because without assumption or engineering model, actually the formula or the equation that you put it there is not valid. So the first assumption here is each component is a control volume, and then the turbine and compressor processes are isentropics, and then there are no pressure drop within the heat exchangers, and then we can ignore the impact of kinetic and potential energy, and the working fluid is air, and it is modeled as an ideal gas. The schematic and TS diagram are shown on the top right side here. So we start solving this problem by specifying the properties at each operating point here at state or at point number 1. So pressure and temperature is given. It is in SI unit. You will use table A22. So find out the enthalpy and PR1 at temperature of 300 Kelvin. So it's pretty small here. So you should be able to get H1 is 300.19 kilojoule per kilogram, and then PR1 is 1.386. So I encourage you, while you are following this class, you also open your table and check each of this number whether they are correct, and it's also help you to be more proficient on reading the table, and it will help you a lot when having an actual exam. And then once we have the properties at state number 1, we go to point 2. So in this case, you will need to get PR2 based on the information of PR1 and P2 over P1. Okay, so this is the relationship that's work for an isentropic process. So PR2 is 10 times PR1, so you will get 13.86, and you need to go back again to table A22 and look at where is the location of this 13.86. So you need to find out two PR numbers in table A22 that brackets this 13.86. So very probably you need to do an interpolation to get H2, and you will get 579.9 kilojoule per kilogram. Okay, so THERMO II, you need to be very proficient with reading the table and then doing interpolation and so on. And then go to operating point number 3. So temperature is given 1400 Kelvin. So you should be able to get H3 and PR3 from table A22 directly. Okay, and I believe you don't need to do interpolation because 1400 Kelvin data is available there. So H3 is 1515.4 kilojoule per kilogram, and then PR3 is 450.5. So, and then go to state number 4, and the way you get PR4 is similar to the one we did to get PR2 here. So PR4 equals to PR3 times P4 over P3, okay? So there is no pressure drop inside the two heat exchanger here, so it's mean P2 over P1 equals to P3 over P4. So it's mean here also that P4 over P3 equals to 1 over 10. Yeah. Okay, then you will get PR4 is 45.05, and then go back again to table A22, and you need to do an interpolation to get H4. So up to this step, we have been able to specify the properties at each point here, point 1 through point 4. Then we are ready to answer the question. The first question is the thermal efficiency of the cycle. So the thermal efficiency equal to what we gain over what we pay. So what we gain here is the network. So this is the turbine power minus the compressor power over Q in. Okay. So here all parameters are per unit of mass basis. So then you get this relationship or correlation. So H3 minus H4, and then minus H2 minus H1 over H3 minus H2. You have all number, just plug in each number in this equation, then you get the thermal efficiency of this ideal Brayton cycle is 45.7%. Second question is the backwork ratio. So this is the ratio of the compressor work to the turbine work. So H2 minus H1 over H3 minus H4. So we'll get 39.6%. So you can look back the topic about Rankine cycle and see what is the backwork ratio for a Rankine cycle, and it is, I believe it's very small, it can be lower than 1%. So the backwork ratio for a gas turbine cycle is much higher than the one for the Rankine cycle. Question number 3, it is the net power developed by the cycle. So this is the net work, right? So it is the turbine power minus the compressor power. So the question is in the unit of kilowatt. So in this case, you need to calculate the mass flow rate. Okay. To calculate the mass flow rate, you can use the ideal gas equation of state. So just pick up state number 1 here. Pressure and temperature is given. Then you should be able to get the specific volume. Okay. And then the volumetric rate is given. So the A times phi, so phi here is the capital, in capital letters, so it is the volume. So A times phi is given. So in the problem, this is 5 cubic meter per second. So to get the mass flow rate, which is in kilogram per second, you need to multiply this by the specific volume. So specific volume, which has the unit of, or you multiply it by the density or divided by the specific volume. Okay, so if multiplied by the density, it is multiplied by the kilogram per cubic meter, or you divide it by the specific volume, which has the unit of cubic meter per kilogram. So in this case, you need to find out or to calculate what is phi1 here. It's in small letters, so the specific volume. So you will use ideal gas equation of state to calculate phi1 here. Phi1 equal to R here with over bar, so it's mean this is the ideal gas, this is the universal gas constant, and then over M here is the molecular weight of air, 28.97, and then times T1 over P1. Okay, so R with over bar here is 8.314 kilojoule per kilomole Kelvin, or it is 8314 joule per kilomole Kelvin. So you just plug in all the number here, make sure that we have a correct unit. Okay, the A time phi is 5 cubic meter per second, and then pressure, you need to convert it to Newton per square meter. So I believe the given unit is in kilopascal. So we have 100, I believe P1 here we have 100 kilopascal. So you need to multiply it by 1000 to get Pascal, and Pascal unit equals to Newton per square meter units. Here you need to multiply it by 1000 to convert the unit from kilopascal to Pascal. And then R here is 8314, so they convert it to be joule per kilomole Kelvin, and then you need to convert kilomole to kilogram, therefore you need to divide it R here by M, 28.97, and temperature is 300 Kelvin. So you will get the mass flow rate of 5.807 kilogram per second. Once you get this M dot, you just plug in this number to this equation. You should be able to get the network in kilowatt here, 2481. Okay. This table is showing the comparison between the air standard analysis result that we look at in the previous slide compared to the result with a cold standard analysis. So in this cold standard analysis, we assume that Cp and Cv and K are constant. In this case, we use K equal to 1.4. Okay, if you use this assumption, so cold air standard analysis. So for the enthalpy difference, for example, like calculating H2 minus H1, you need to replace it by Cp times T2 minus T1. Okay, similarly for H3 minus H4, so this is the turbine power per unit of mass, so you need to get this one from Cp times T3 minus T4. Okay, and then you also have the correlation between the pressure ratio and temperature ratio, so that you can get T2 and so on. So you can see in here, if we use cold air standard analysis, we get the network of 2308 kilowatt, while for the air standard analysis we got 2481. So there's some decent difference there between these two analyses. The next topic is looking at the effect of compressor pressure ratio on performance. So we have a PV diagram here. On the right side we have TS diagram. So if we increase the compressor pressure ratio, then point 2 in the TS diagram here will move up. So it will move up. So we have a new point at the compressor exit here is point 2 prime here. So P2 prime is higher than P2. So this means here we have an increased pressure ratio inside the compressor. And then from point 2 prime going to point 3 prime, it is the process inside the heat exchanger. So by doing a cold air standard analysis, you will be able to get the correlation between the thermal efficiency of the system and the P2 over P1. It is equation 9.25. And the way it is derived, it's similar when we look at the correlation between the compression ratio and engine efficiency in Otto cycle. So equation 9.25. If you plot this relationship, you will see how does this P over P1 impact eta. The effect of compressor pressure ratio on the thermal efficiency is shown in this right figure. So the horizontal parameter here is the compressor pressure ratio, and this one is the thermal efficiency. And the line showing the relationship of the pressure ratio to the thermal efficiency is this line. So as you can see, as the compressor pressure ratio increases, the thermal efficiency increases as well. So if we want to maximize the thermal efficiency, we need to maximize the compressor pressure ratio. However, in actual system design, there is a limitation, which is the strength of the material for the turbine as well as the heat exchanger. And one of these limitations is the maximum temperature. So looking at the gas turbine system, the maximum temperature is at T3, which is the entrance of the turbine or at the exit of the heat exchanger. So once the T3 is specified, we can have two scenarios on designing a gas power system. The first scenario is the one that can maximize the thermal efficiency. So on the left side, you have a TS diagram here. If I want to maximize the thermal efficiency, then I should design a system consisting of point 1, point 2 prime here, and then point 3 prime here. This is the temperature limit, so let me put here, this is the Tmax. Okay, and then point 4 prime. So this is the system design for a high thermal efficiency. Why it has a high thermal efficiency? Because I maximize the TH. So remember, the Carnot efficiency is 1 minus TC, T cold, over TH. So in this first scenario, which is called cycle A, I have a high TH and I have a low TC. So I have two good things here, which can maximize eta. And on the second scenario, in this case, I can sacrifice some of the thermal efficiency number, but I will get a higher network per unit of mass flow. In the second scenario, which is called cycle B, I have the system design consisting of, I put purple line here is 0.1, 0.2, and then 0.3. So you can see in here T3 equal to T3 prime, which is the maximum temperature, okay? And then 0.4 here. If you compare the area surrounded by the process line, the second scenario has a larger area, which means it has a larger network per unit of mass flow. What does its impact to the system is that the system size will be smaller. It's more compact. Okay, but once again, the second scenario, which is called cycle B, has a lower thermal efficiency. Why it has lower thermal efficiency? If you compare the cycle B with cycle A, cycle B has a lower TH, okay, because the TH for cycle B will be the average between T2 and T3. So lower TH means lower eta. Second one, cycle B has a higher TC, okay, has a higher TC because the TC for cycle B is the average between T1 and T4, okay, and higher TC means it's also a lower eta. Okay, so depending on the purpose of the system design, whether we want to have a maximum thermal efficiency or we want to have a smaller size, it will drive the direction of the design. So the design A, once again, is intended to have a system with higher thermal efficiency. And so in this case, the size doesn't matter. And cycle B here is designed to have a small system, a lighter system, which is very good for example, aircraft. Okay, if you want to design a gas turbine for aircraft, you can sacrifice some of the thermal efficiency, but you will get a very light system, and you need to select cycle B. Okay, cycle A, maybe you would like to use a gas turbine for a stationary power station. So in this case, it doesn't matter what is the size of the system. The goal is to have a higher thermal efficiency. The next one is considering gas turbine irreversibilities and losses. So in actual system, we will see some losses at each of the component. For example, the process inside the turbine and inside the compressor is not isentropic process. So you will have, or you will see the production of entropy at the exit of each component. In the TS diagram here, the actual process inside the compressor, you will have a dash line here connecting point 1 to point 2. So you can see there that S2 is higher than S1. But if it is isentropic process, you will have a solid line connecting point 1 to point 2S. So S2S equal to S1. And this irreversibility coming from maybe friction inside the compressor, and also the compression process is not adiabatic. So these two things increase the entropy. And then inside the turbine, we also have a friction, and then the process is not adiabatic. So it means it is not an isentropic process. So the actual process here is represented by the dash line connecting point 3 to point 4. So S4 has a higher So S4 is higher than S3. And then inside the heat exchanger, you will have also a pressure drop. You will have a pressure drop, so it means as P3 will be lower than P2. So you see here in the TS diagram on the left side. So we have a small drop of the pressure here. So P3 is lower than P2, and similarly you will see that P4 is higher than P1. But usually the pressure drop inside the heat exchanger is smaller compared to the losses inside the compressor and the turbine, so that in this analysis, so in THERMO II, all of the problem assume pressure drop inside the heat exchanger is 0, so it means P3 equal to P2, and then P4 equal to P1, so it is on the right side. So this is the TS diagram that we will find out in this THERMO II. So we might have some irreversibility given in the problem inside the compressor and turbine, so that you have a dash line connecting point 1 to point 2 as well as point 3 to point 4. And if it does, you will get the parameter here, which is the turbine efficiency and the compressor efficiency. And I believe this equation is not new for you. So for example, the turbine efficiency here is the ratio of the actual turbine power over the isentropic power. Okay, let's take a look on this example. It is example 9.6 in the textbook. So this example is similar to the previous example. For example, like here the air entered the compressor at 100 kilopascal and temperature 300 Kelvin, and then volumetric flow rate is also 5 cubic meter per second here, and then the compressor pressure ratio is 10. What is new here is that now we incorporate the turbine and compressor efficiency, so 80%. The equations stay the same, so the thermal efficiency and then backwork ratio and the net power developed in kilowatt. This is the TS diagram along with the assumption. Once again, when you solve a problem, you need to put the assumption of engineering model. Otherwise, the formula that you use there are not valid. Okay, this is a TS diagram because there is irreversibilities inside the compressor and turbine. You have a dash line here connecting point 1 to point 2 here. Okay, this is inside the compressor, and then inside the turbine you have point 3 here and point 4 here, and then 2s and 4s are shown here for an isentropic process. This is the engineering model. So each component is analyzed as a control volume at steady state, and then the compressor and turbine are adiabatic, but they have irreversibilities. And then there are no pressure drops for flow through the two heat exchanger, and then we can ignore the impact of the kinetic and potential energy change. And then the working fluid is air, and it is modeled as an ideal gas. So to calculate the thermal efficiency, you need to know what is the turbine power, actual turbine power after we incorporate the efficiency, and then actual compressor power and Q in. Okay, so in the previous example, we already got what is, for example, like H1, and then we know H2S, so we need to calculate H2, and then we know H3, and then we also know H4S, so that we need to calculate H4. Okay, so to calculate turbine power, so you need to calculate the turbine power at isentropic process times the turbine efficiency. And the turbine power per unit of mass from the previous example is here 706.9. You multiply by 0.8, so this is 80% of the turbine efficiency. You will get the turbine power of 565.5 kilojoule per kilogram. And then for the compressor, we got the isentropic work from the previous example. So for the compressor, the actual work, you need to divide it by the compressor efficiency, which is also 0.8 or 80%. So because of this irreversibility, you will see that the turbine power decreases and the required power by compressor increases. You get two double negative impact here to the system performance because of irreversibilities. And the impact, for sure, the thermal efficiency of the system will be lower than the one from the previous example. So by using the compressor efficiency correlation, you will be able to get what is H2. So H2 here is 649.8 kilojoule per kilogram. And then you know what is Q in. Okay, so H3 stay the same as the previous example, but you have a new H2 here. So once you have the actual turbine power, actual compressor power, and then the new Q in, you should be able to get the thermal efficiency. It's only 24.9%. So looking back the previous example, it is for sure it is higher than 24.9%. And then the backwork ratio increases now to 61.8%. Okay. And then the last question is the network. So now it is 1254 kilowatt. The next topic is regenerative gas turbines. So the idea of this regenerative is similar to the one we had in the vapor cycle. The idea behind having a regenerative gas turbine system is that the gas exiting the turbine at point 4 here is still hot, and it will be useful to utilize this hot gas to heat up the mixture, especially before it enters the combustor. And to have this regenerative type system, we need to have additional component, and this is called a regenerator. And this regenerator is a kind of a closed heat exchanger. So the mixture enter the compressor at point 1, and then we have point 2 here at the exit of the compressor. Then before it enters the combustor, this mixture will get a heat transfer inside the regenerator coming from the hot gas. So before it enters the combustor, the state is at X, which is hotter than the temperature at state 2, and thus the required Q in, this is what we pay, to get a targeted temperature at T3 is lower. On the right side is the TS diagram. So we have point 1 entering the compressor, and then point 2, and then there will be a heat transfer inside the regenerator that changes state 2 to state X. So you can see here that Tx is higher than T2, and this energy is coming from the mixture that exit the turbine. So in this case, at the exit of the turbine, we have state 4 here, and then because there will be a heat transfer from the mixture at state 4 here inside the regenerator, then the energy of this, which is mainly the burn gas, decreases, and at the exit of the regenerator, it is state Y here. So Ty is lower than T4. And usually it is assumed that the process inside the regenerator doesn't have a pressure drop, therefore Px equal to P2 as well as P4 equal to Py. So with this regenerative type setup, once again, we will have the same net power, because the condition inside the turbine and inside the compressor do not change, while the Q in decreases, because Q in is required to heat up the mixture from state X to state 3, and thus the efficiency of the system increases. In actual regenerators, which is once again a closed heat exchanger, there will be a delta T between the hot stream, and this one is coming from the turbine, this one. There will be a delta T between the hot stream and the cold stream. Okay, and the typical delta T for a regenerator is shown in this A. So we have a hot gas temperature profile, so this one, and then we also have a cold gas temperature profile, and there will be a delta T here between the T hot and T cold. For the ideal heat exchanger or ideal heat transfer, where we have infinite surface area, so the temperature difference between these two streams will be smaller, or ideally it will approach zero. So this happens when the surface area is infinite. So if we have this ideal condition, then you can see on the right side here that the delta T approaches zero. This means at the exit here, the temperature of the cold stream equal to the temperature of the hot stream at the inlet. So it's mean here at the inlet the T hot equal to T4, okay, at the inlet, and then at the exit of the cold stream side, T cold equal to Tx. So this means for an ideal condition where surface area of the heat transfer is infinite, T4 equal to Tx. Okay. Because of this ideal condition, then we can apply a new parameter which is called Regenerator Effectiveness, that's showing the ratio of the actual performance to this ideal performance. And this is the formula. So the regenerator effectiveness is once again the ratio of the heat transfer, or the ratio of the condition between the actual to the ideal condition. So in the actual condition, the enthalpy at the exit of the cold stream is Hx. Okay. For the ideal condition, the enthalpy at the exit of the cold stream equals to the enthalpy at the state of 4, so H4, and this is the formula. And in typical regenerator, the effectiveness is between 60 to 80%. So if we want to have a better system improvement for a gas turbine, then we need to have a better regenerator performance. So in this case, the regenerator effectiveness need to be higher. So this also means that we need to increase the surface area of the regenerator. Increasing the surface area of the regenerators also means increasing the pressure drop. Okay, so there will be a negative effect. Beside, for sure, we will have a higher heat transfer. So the addition of this heat regenerator to a gas turbine is finally limited by this pressure drop as well as the price of the regenerator, because a bigger regenerator costs more money. So at some point it might not be economic to include regenerator in a gas turbine, because the efficiency improvement is smaller than the increase of the capital cost. Let's have a look on this example. So this example is 9.7 in the textbook. So we will use the previous example, so example 9.4, and in this example 9.4, I believe this is a standard Brayton cycles. We only have component of compressor and then combustor and turbine, and we incorporate a regenerator in this example, and then we will see what will be the thermal efficiency of the system. And the regenerator effectiveness is also given here, 80%. And then we need also to plot the thermal efficiency as a function of the regenerator effectiveness from 0 to 80%. This is the schematic of the system. So on the left side, so we have a compressor and then a regenerator. So it has effectiveness of 80% here. And then we have the combustor. We got a Q in here to change the state from X to 3. And then the turbine will do an expansion process. Some of this power will be needed to drive the compressor. The rest will be used to do other purposes. And then on the right side is the TS diagram. So state 1 is at the turbine inlet, and then at turbine exit we have state 2, and then due to the heat transfer inside the regenerator, the state 2 here changed to state X, and then entering the combustor because of the heat transfer, because of the Q in, state X changed to state number 3, and then entering the turbine, there will be an expansion, the pressure drop, temperature drop to state number 4, and then entering the regenerator, the temperature drop from state 4 to state Y here. There is no pressure drop inside the regenerator, so Px equal to P2 as well as P4 equal to Py, and pressure at the low side is 100 kilopascal or 1 bar, and then at the high side we have 1000 kilopascal. So here the pressure ratio is 10, and then T1 is given there, 300 Kelvin, T3 is 1400 Kelvin. This is the assumption or the engineering model. So each component is analyzed as a control volume at steady state, and then the process inside the compressor and turbines are isentropic, and then there are no pressure drop for the flow through the heat exchanger. So it's inside the regenerator and inside the combustor, so there is no pressure drop. And then the regenerator effectiveness is 80%, and then we can ignore the impact of kinetic and potential energy change. And the last assumption is that the working fluid is 100% air and can be modeled as an ideal gas. So the first step is also we need to determine the state properties at each point. So H1 we know it from the previous example, so temperature 300 Kelvin. So using table A22 we'll get H1 is 300.19 kilojoule per kilogram, and then H2 by using the correlation of the pressure ratio to the PR ratio we will get 579.9 kilojoule per kilogram. H3 is based on the T3 of 1400 Kelvin. We get 1515.4 kilojoule per kilogram, and then H4 is 808.5 kilojoule per kilogram. So the next step is to determine the enthalpy at state or at point X. So in this case we will use the correlation of the regenerator effectiveness. So the eta here is 80%, and H2 we know this one, H4 also we know, so we should be able to get the enthalpy at a state or point X here. So 762.8. So you can see in here, if we don't use the regenerator, the enthalpy at the combustor entrance or the heat exchanger entrance will be H2. So 579.9 kilojoule per kilogram. And then by using the regenerator, the enthalpy at the entrance of the heat exchanger increases to 762.8 kilojoule per kilogram. Okay, the next one is to calculate the thermal efficiency of this regenerative gas turbine system. So this is the ratio of the net power over Q in. So we have H3, H4, H2, H1 as well as Hx, so that we can get the thermal efficiency now is 56.8%. So you can compare this thermal efficiency with the one in example 9.4, and I believe this efficiency is higher. And then you can make a plot of the thermal efficiency as a function of the regenerator effectiveness. So in this case, you need to replace the parameter Hx in the thermal efficiency formula by the regenerator effectiveness. And then you can see in here, when we increase the regenerator effectiveness from 0 to 80%, the thermal efficiency increases here from around maybe here is 40.46, so it is 46%. So it's just a rough estimation here, to I think it is somewhere close to 60%, so this might be 57%. So increasing the regenerator effectiveness increase the thermal efficiency, but as I mentioned to you, that it will require a larger surface area, which also means a higher pressure drop, and this also means an increase of the capital cost. So at some point it might not be economic to have this thermal regenerator, because the thermal efficiency improvement is smaller than the increase of the capital cost. And I believe there is one course that discuss about the correlation between the system performance and the economic capital cost and so on. It is thermal system design, and I believe it is at the 4th year of this mechanical engineering class. The next topic is regenerative gas turbines with a reheat and intercooling. So we just discussed about a regenerative gas turbine, and then we'll combine this method with reheat and intercooling. So the first topic is about gas turbine with reheat. So the idea behind having this reheat is that if you look at the constant pressure line in the TS diagram, as we go to the right side, so this line diverge, so it's mean we will have a larger turbine power when we go to the right. So this is the idea, having the reheater or having a reheat system in the gas turbine power system. So in this case we have a compressor. So, and then we have the first combustor that got a Q in from external source, and then we have the first turbine type here. So this is high pressure turbine. It's also called turbine stage 1. It produces the power. Some of this will be used to drive the compressor, the rest will be used to do other purposes. And then at the exit of this turbine state 2, the pressure is not the same as P1, rather it is expanded to a certain intermediate pressure, and then the mixture is reheated inside the second combustor here, which is called a reheat combustor. It got another Q in here, and then because of this additional Q from external source, the temperature increases from TA to TB. And then at TB, the mixture enters the second turbine. It's called turbine stage 2. And then at the exit of the last turbine here is state 4. So the TS diagram is on the right side here. We have point 1 and then point 2 here at the exit of the compressor. And then because of the Q in from the first combustor, the temperature increases to T3 here. And there will be an expansion inside the turbine stage 1. The temperature and pressure drop to state A here. Okay. And then at the state A, the mixture is reheated to state B here, okay, at constant pressure, because there is no pressure drop inside the combustor as well as inside the reheat combustor. And then once it is reheated, the mixture is directed into the turbine state 2. And then there will be additional power here inside the turbine state 2, and then the mixture at the exit of the last turbine here is state number 4. So once again, if you see these two constant pressure line, so the first one is this one, second one is this one. As we go to the right, these two lines diverge. So it's mean the turbine power increases as we have two-stage turbine compared to if we have only one turbine. So once again, this is because the length of this line, so let me say here, the length of the line connecting point 3 to point 4 prime here is shorter than the length connecting point 3 to point A plus the line connecting point B to point 4 here. So once again, by having a reheat combustor, the net power of the system can be increased, but the thermal efficiency of the system would necessarily increase because we need additional Q in here. A good thing from this gas turbine with reheat is that the chance to utilize the gas at the turbine exit by having a regenerator increases compared to the one without reheat combustor. So compare the condition between state 4 prime and state 4 here. Without a reheat combustor, at the exit of the turbine will be at state 4 prime. By having a reheat combustor, the state at the turbine exit will be state 4 here. And you can see here the temperature at state 4 is higher than the one at state 4 prime. Therefore, once again, the chance or the energy that can be taken from this hot gas inside the regenerator is higher by having a reheat combustor. And you will expect that if we combine this reheat with a regenerator, the thermal efficiency increases significantly. Let's take a look on this example. So once again, we will consider equation example 9.4. So the state stay the same. At the entrance of the compressor, we have 100 kilopascal and 300 Kelvin, and then it is compressed to 1000 kilopascal. So it's mean the pressure ratio inside the compressor is 10, and then the temperature at the inlet of the first turbine stage is 1400 Kelvin. It is also stay the same. And then the expansion takes place isentropically at two stages here, with reheat to 1400 Kelvin again. So we will have a reheat combustor that reheat the gas back to 1400 Kelvin before it enters the second stage of the turbine. Okay, and the intermediate pressure is 300 kilopascal. And in this problem, we can assume that the regenerator effectiveness is 100%. So the question is, what is this thermal system efficiency? And this is the TS diagram. So we have state 1 at the entrance of the compressor, and then at the exit of the compressor we have state 2, and then state X. This one is at the exit of the regenerator, and because the effectiveness of the regenerator is 100%, Tx equals to T4. This is very important. So T4 here is at the exit of the last turbine stage, and also this is at the entrance of the regenerator. Because the effectiveness is 100%, Tx equal to T4. So you can see in here that X, if you draw a line connecting X and 4, it will be a horizontal line. And then at the entrance of the first turbine, it is state 3. The temperature is given there, 1400 Kelvin. And then inside the first turbine, the pressure dropped from 1000 kilopascal to 300 kilopascal. So this is state A here. And then the mixture is reheated back to 1400 Kelvin again, state B here. Okay, and then at the last turbine, there will be an expansion that changes state B to state 4. Okay, and you don't need to consider the state at the exit of the regenerator from the hot side because you don't need it. And the right side is the engineering model. So its component is analyzed as a control volume at steady state, and then the process inside the compressor and turbines are isentropics, and then there are no pressure drop for flow through the heat exchanger. So we have two heat exchanger. One is the main combustor, and then we have three heat exchanger. Okay, so one is the main combustor, second one is the reheat combustor, and the third one is the regenerator. And then the regenerator effectiveness is 100%, and then we can ignore the effect of the kinetic energy and potential energy, and the working fluid is air and can be modeled as an ideal gas. Okay, the first step is to determine the state at each point, the properties at each point. So state 1 to 3, I believe it is the same as the one from the previous example. So we have H1 300.19, H2 is 579.9, and H3 is 1515.4 kilojoule per kilogram. And then the temperature at state B equal to the temperature at state 3, so it's mean HB equal to H3. Okay, and then to calculate the properties at state A, so state here is at the exit of the first turbine, we can use this correlation, so isentropic correlation. So this is the correlation between the pressure ratio to the PR ratio. So PA over P3 here is 300 over 1000, and then PR3 can be obtained from table A22. So you will get PRA here is 135.15, and then you go back again to table A22 to get what is the enthalpy at state A. So you will get 1095.9 kilojoule per kilogram. Okay, and then to get the enthalpy at state 4, this is at the exit of the second turbine, you can use the same correlation here. correlation between pressure ratio and PR ratio. So in this case, you will use P4 and PB. So PB is 300 and then P4 is 100 kilopascal, and PRB is PR at 1400 Kelvin. So it is 450.5. So you will get PR4 here is 150.17, and then you go back again to the table A22 to get H4 here by an interpolation. And then since the regenerator effectiveness is 100%, so it's mean that Tx equal to T4, so it also means that Hx equal to H4. So you get all the enthalpy at each state or at each point, then you are ready to calculate what is the thermal efficiency. So in this case, you will get the thermal efficiency of the system using a reheat combustor as well as regenerator. It is 65.4%. And I remember in the last example, when we only have a regenerator, the system efficiency is only 56%, I believe. So you can see there's an increase of around 9% when we incorporate a reheater and a regenerator. The next topic is compression with intercooling. This is the PV diagram of a compression process inside a compressor with its control volumes. It means it is an open system, so there will be a mass flow in and out of the system. Why I put this statement? Because there is also a compression process inside a closed system, for example, like inside the piston cylinder system. And in this compression process, there is no mass flow in and out. So for the compression process inside a control volume, so in this case a compressor, the area on the left side of the process line represent the required compression work. So first take a look on the process line connecting point A, so this is at the entrance of the compressor, and point 2 prime. So this process line is an adiabatic compression, so it means there is no heat transfer during the compression process. So the area surrounded by point 1 and then 2 primes, let me put here is point A and then point B, represent the required compression work. So it means it is the work needed by the system to do a compression process. This is what we need to pay. And then assuming that we have a cooling during the compression process, then the process line will shift to the left. So we have the second process line here connecting point 1 and point 2 here. So this is a process line of compression with cooling. So the area surrounded by point 1, point 2, and then A and B here represent the required compression work. So this is the work that need to be inputted to the system, what we pay. So you can see in here that if we can have a compression process with a cooling, then the required compression work decreases. This also means the system efficiency increases. And this is the formula to estimate the compression work. So this integral from point 1 to point 2 phi dP. Okay, so keep in mind phi dP. This is an open system or control volume system. So this means once again, if we can apply a massive cooling inside massive cooling during a compression process, we can shift this compression line or process line to the left. So it means we will have less compression work. But unfortunately, it is not easy. It is not easy to apply an efficient cooling while we only have one state of the compression process. One of the common way to apply a cooling process during the compression is by having a multi-stage compression. So in this case, we can have maybe 2-3 compressor and then put an intercooler in between. So this picture is showing the schematic of the system with two-stage compression. So we have compressor stage 1 and compressor stage 2, and between these two compressors we insert an intercooler here. So at the entrance of the first compressor we have point 1 here, and then the working fluid is compressed to state C. Okay, and then you can see also in the TS and PV diagram we have state 1 here, and then it's compressed to state C. Okay, and then before it enters the second compressor, the mixture is cooled inside the intercooler so that state C change to state D. Okay, state D here. So temperature at state D can be the same as temperature at state 1. Okay, and then in the PV diagram I have state 1 here, and then I have a isentropic process inside the compressor that changes state 1 to state C. Okay, and then before it's enter the second compressor, it is cooled inside the intercooler that change the state C to state D. And then we assume that there is no pressure drop inside the intercoolers, and that PC equal to PD. And then from D, the working fluid enter the second compressor, and then it's changed from state D to state 2 here. So with this multi-stage compression, the process inside the compressor is still isentropic process, but you can see the benefit of the area reduction because of this multi-stage compression option. And the area reduction here is represented by this one, by this area, this one. Okay, if we don't have intercooler, so it's mean state 1 will go to state 2 prime here, because the target is a certain pressure ratio. So you want to have a certain pressure ratio target here from state 1 to state 2 prime, and P2 prime equal to P2. Okay, by having an intercooler, now you change state 1 going to state C, and then there will be intercooling or a cooling process that change state C to state D, and then from state D it is compressed to inside the second compressor to state 2. And then by looking at the area in the PV diagram, you will see less area when we have an intercooler inside the system. Okay, so but there is a drawback of this intercooler in case you only use intercooler in the gas turbine system. At the entrance of the combustor, the temperature of the working fluid decreases from state 2 prime to state 2. So it's mean you need more Q in, okay, to bring this mixture from state 2 to state 3. So you have a certain targeted temperature at the exit of the combustor, okay, with the state 3. So but in mind, if we combine this intercooling type option with the regeneration type option, then the propensity or the chance to get the heat transfer from the mixture that exits the turbine increases. Why? Because at the entrance of the regenerator we have a cooler temperature, which is a T2 rather than T2 prime. So it means you have a larger temperature difference between the cold stream and hot stream inside the regenerator, so you will have more heat transfer. Okay, so once again, if you want to get a maximum benefit of using this intercooling option, you need to combine it with a regenerator. Let's take a look on this example. So we will evaluate a two-stage compression with intercooling, and let's see whether it will be combined with a regenerator. Okay, let's read this example statement. Air is compressed from 100 kilopascal 300 Kelvin. So I believe this is state number 1 equals to the state 1 in previous example, in two-stage compressor with intercooling between stages, and the intercooler pressure is 300 kilopascal. The air is cooled back to 300 Kelvin in the intercooler before entering the second compressor stage. Each compressor stage is isentropic, and then for steady state operation and negligible change in kinetic and potential energy from inlet to exit, determine the temperature at the exit of the second compressor stage, and then B is the total compressor work input per unit of mass flow, and then C is repeat for a single stage compression from the given inlet state to the final pressure. Oh, okay. So this problem is just try to focus on the two-stage compressor with intercooling. Okay, on the left side is the schematic of the system. We have two compressors here, compressor stage 1 and stage 2, and in between there is an intercooler. Okay, this intercooler make the temperature back to 300 Kelvin. So at the entrance of the compressor stage 1, T1 is 300 Kelvin, and because of the compression process, the temperature will increase at stage 3, and then inside the intercooler, the temperature will be back to 300 Kelvin again at TD here, at state D. And then at the exit of compressor state 2, the pressure is 1000 kilopascal. And on the right side is the PV diagram. We have state 1 at the entrance of the compressor stage 1, and then C is exit of the compressor stage 1, D is the exit at the exit of the intercooler, and then 2 here is at the exit of the compressor stage 2. And we also need to compare the compression work in case we only have one compressor. So it's mean in case we have state 1 here and it is changed directly to state number 3 here. Okay, and this is the engineering model or assumption. So the compressor stage and intercoolers are analyzed as control volumes at steady state. Okay, so control volume steady state, and then the compression processes are isentropic, and then there is no pressure drop for flow through the intercooler, and then we can ignore the impact of the kinetic and potential energy change, and then the working fluid is air and can be modeled as an ideal gas. So we have state 1 here, temperature and pressure is given, so we can get what is H1 and PR1, and then we can also get PR2 here from the given temperature at point D. So because the temperature at point D is 300 Kelvin, so we can get PR2 and thus the enthalpy at point 2. Okay, so we know that P2 over PD, so this is 1000 over 300 kilopascal, and then PRD is 1.386, so you get PR2 is here is 4.62, and then using table A22 you will get T2 is 422 and H2 is 423.8 kilojoule per kilogram. Okay, I think it should be easier to get the state at the exit of the compressor stage 2. Okay, the next one is to estimate the compressor work. First is if we have two-stage compressor here, the compressor work will be Hc minus H1. So this is the required compression work from the compressor stage 1 plus H2 minus HD. So this is the required compression work from compressor stage 2. Okay, and then we have H1, we have H2, And then HC, you can get it from the correlation of the pressure ratio, so, and PR ratio. So PC over P1 here is 300 over 100, so it's 3. And then PR1, you can get it from table A22 at 300 Kelvin. So you will get PRC here is 4.158. So once you get PRC, you should be able to get the enthalpy at C here. This is 411.3 kilojoule per kilogram. Okay, so you have H1, you have H2, and then HD, you also have it because temperature HD equal to temperature at 1, so HD equal to H1. Okay, so you will get the required compression work with two-stage compressor here. So it is 234.7 kilojoule per kilogram. Next one is we need to compare this value in case we only have one stage compressor. So it will be for sure higher than 234.7 kilojoule per kilogram. And in this case, you need to get the enthalpy at state 3 here. So you use a correlation of the pressure ratio to the PR ratio to get PR3. So P3 over P1 is 10, and then PR1 is 1.387. So you will get PR3 is 13.86. And then using table A22, you need to do interpolation. You will get T3 is 574. Okay, so this one is higher than T2, and you will get H3 is 579.9 kilojoule per kilogram. And this is the required compression work in case we only have one compressor, 279.7. So it's much higher than the one with two-stage compressor. Okay, so you can see in here that this simple example confirms that using two compressor plus an intercooler required much lower compression work compared to the one using only one compressor. So for sure, from other perspective, like the economic perspective, the system with intercooler and two compressor required more capital cost. The next example is to determine intercooler pressure for minimum total compressor work. So this is the example statement. So for two-stage compressor with fixed inlet and exit pressure, conduct a cold air standard analysis to express in terms of known property values the intercooler pressure required for the minimum total compressor work per unit of mass flowing. We can assume steady state operation and the following idealization. So each compression process is isentropic, and then there is no pressure drop through the intercooler, and then the temperature at the inlet to the second compressor is greater than or equal to that at the inlet to the first compressor. Then we can also ignore the effect of kinetic and potential energy. Let's see the solution of this example. On the left side is the schematic of the PV diagram. So the entrance to the first stage compressor is 0.1 here. And then PI is a variable that we need to determine here. And then the line connecting point 1 to point C here is the isentropic process line. And then we also have a process line in case the temperature is constant or isothermal. This is the black line here, this one. Okay, and this is state 2. Okay, and on the right side is the engineering model of this problem. So the compressor stage and intercooler are analyzed as a control volume at steady state, and then the compression process are isentropics, and then there is no pressure drop for flow through the intercooler, and then the temperature at the inlet to the second compressor stage obey TD here is greater than or equal T1. Okay. And then number 5, we can ignore the effect of kinetic and potential energy, and then the working fluid is air and can be modeled as an ideal gas. And then assumption number 7 here is that the specific heat Cp and thus the specific heat ratio are constant. And then the first equation shown here is the total compressor work input per unit of mass flow. So this is the sum of the first compressor work and the second compressor work. The first compressor work here is Hc minus H1, and then the second compressor work is H2 minus Hd. The next step is we can replace the enthalpy formula by Cp times T, or if it is delta H, then it is Cp times delta T. So you have this formula, and then you manipulate it slightly. So in this term, you multiply it by T1 and then divide by T1 for the one inside the bracket. Similarly, on the right, on the second term here, you multiply Cp by Td and then divide each term inside the bracket by Td. Okay, so you have this formula, and then since the compression processes are isentropic and the specific heat ratio K is constant, then you can use isentropic correlation between the temperature ratio and pressure ratio here. So Tc over T1 equal to Pi. Pi is the intermediate pressure that we will optimize here, equal to Pi over P1 to the power of K minus 1 over K. Similarly, you will get the correlation between T2 over Td to the P2 over Pi to the power of K minus 1 over K. And then you can replace the correlation for Tc over T1 and T2 over Td with this correlation. Okay, then you will get this one. Okay, hence for specified value of T1, Td, P1, P2 and Cp, the value of the total compressor work input varies with the intercooler pressure only. So the intercooler pressure here is the Pi. So in this case, to determine the Pi that minimize the total work, so we need to apply the derivative process of this compressor work per unit of mass flowing. So we derive this one to Pi. So you will just need to follow this step. So you will look at that dW over m over dPi equal to this formula. Okay, and then if you set this partial derivative to 0, then you will get this correlation A, or you can modify it slightly to get correlation B here. And then if you do one more derivation, so you will get the second derivation, so you will see that the Pi with this correlation B is the one that will produce minimum compressor work. So once again, to get the minimum compressor work, Pi should be to the value of equation B here. So it is a function of Pi, P2, and then TD, and T1, and then K. Next one is a gas turbines with reheat and intercooling. So having a reheat and intercooling together, we will get two advantage. Okay, so the first advantage is that the network output is increased. Okay, why the network output is increased? Because we'll have less compression work. And the second one is that the potential for regeneration is enhanced. Okay, why the potential for regeneration is enhanced? First is by having an intercooling, the temperature will be at 4 here. Okay, will be at 4 here. But if we don't have an intercooler, the temperature at the exit of the compressor will be somewhere here. Okay, and then on the right side, by having a reheat, the temperature at the exit of the turbine will be hotter. So it will be at 0.9 here instead of 0.10. Okay, so you can see in here that at the entrance of the regenerator from the hot stream side, the temperature is hotter, temperature is higher, and then at the entrance to the reheater from the cold stream side, the temperature is colder. So we have a larger delta T between the hot stream and the cold stream. Therefore, the potential for regeneration is enhanced. So accordingly, when reheat and intercooling are used together, okay, with regeneration, so we expect a substantial improvement in performance of the corresponding system. Okay, and this figure is showing the schematic of this arrangement. So where we have an intercooler here, and then we have a reheater here, and then this is a regenerator. So with this system set up, it is expected to have a substantial improvement in performance. Let's have a look to this example. So example 9.11 in the textbooks. A regenerative gas turbine with intercooling and reheat, so it's combined together, intercooling and reheat, operates at steady state. Air enters the compressor at 100 kilopascal, 300 Kelvin. So this is state 1, so same as the one in the previous examples, with a mass flow rate of 5.807 kilogram per second. The pressure ratio across the two-stage compressor is 10. And then the pressure ratio across the two-stage turbine is also 10. The intercooler and reheat each operates at 300 kilopascal or 3 bar. At the inlet to the turbine stage, the temperature is 1400 Kelvin. The temperature at the inlet to the second compressor stage is 300 Kelvin. So it means it is cooled back to T1. The isentropic efficiency of each compressor and turbine stage is 80%. The regenerator effectiveness is 80%. The question determine the thermal efficiency, and then the backwork ratio, and then C is the net power developed in kilowatt, and then D is the total rate of energy added by heat transfer in kilowatt. Let's take a look on the solution of this example. This is the schematic of the system, pretty much the same as the one in the previous slide, but in here you can see the number for certain state or operating point. So at point 1, it is entrance to the first compressor. T1 is 300 Kelvin, and then P1 is 100 kilopascal, and then the mass flow is 5.807 kilogram per second, and then P2 equal to P3, so because we can ignore the pressure drop inside the intercooler. So P2 equal to P3 equals to 300 kilopascal. And then at the exit of the second compressor, it is 0.4, and P4 equal to P5 equal to P6. So here we ignore the pressure drop inside the regenerator and the combustor. So P4 equal to P5 equal to P6 equal to 1000 kilopascal. Okay, and then at the exit of the regenerator from the cold stream size is state number 5, and then at the exit of the combustor before it's entered the turbine 1, state is number 6. I believe T6 is given 14, here is 1400 Kelvin, and then we have state 7 here at the exit of the turbine 1, and then entering the reheater, it is reheated to state number 8. So I believe temperature at point 8 equal to the temperature at point 6. It is 1400 Kelvin. Okay, and then P7 equal to P8, it is 300 kilopascal. And then this is state number 9 at the exit of the turbine 2. And then there is internal irreversibility inside the compressors and turbines. Therefore, in the TS diagram, you see dash line here. This is in the first compressor, second compressor. This is first turbine and second turbine. You see the dash lines. It's meaning that the process inside the compressor and the turbines are or the process has some internal irreversibility. And on the right side is the list of the assumption or engineering model. So each component is control volume at steady state, and then there are no pressure drops for the flow through the heat exchangers. So we have several heat exchangers here. So intercooler, regenerator, and then combustor, and then reheat combustor. And then the compressor and turbines are adiabatic. So it is adiabatic, but there is internal irreversibilities. And then we can ignore the impact of kinetic and potential energies. And then the working fluid is air and can be modeled as ideal gas. Okay, the way we determine the properties at each stage or at each operating point is pretty much the same as the one we saw in the previous example. So in this case, we don't need to repeat that process again. Rather, you can see in here we have a table showing the enthalpy at different states. So starting from state number 1 up to state number 9. Okay, we don't need to consider state number 10. It is at the exit of the regenerator from the hot stream side because we don't need it. Okay, once we are done specifying this enthalpy at each state, then we are ready to answer the question. I believe the first question is the thermal efficiency. So the first step here is to calculate the turbine power. So we have two turbines. So the turbine power per unit of mass flowing from the first turbine is H6 minus H7. So here. And then from the second turbine, it is H8 minus H9. Okay, you have all H number here, and you just plug in, you will get it. So it is 645.8 kilojoule per kilogram. So this is the turbine power. And then the next one is to calculate the total compressor work input per unit of mass flowing. So we have two compressors. So from the first compressor, the work is H2 here minus H1, okay, and then from the second compressor it is H4 minus H3, okay. So keep in mind, in this solution we maintain all number positive, so that although we know that the compressor required work from outside, so we maintain the number here as positive, okay, just to avoid confusion. So the total compressor work input per unit of mass flowing, it is 293.4 kilojoule per kilogram. And the next one is to calculate the Q in. So we need a Q in inside the combustor as well as the Q in inside the reheat combustor. From the first combustor, the Q in is H6 minus H5, and then from the reheat combustor it is H8 minus H7. So you just plug in the number, you will get 795.9. So we got the compressor work, we got the turbine work, we got the total Q in, then we can calculate the thermal efficiency of the system. So it is 44.3%. And then the backwork ratio is just the ratio between the turbine work to the ratio between the compressor work to the turbine work. So it is 45.4%. So it's pretty high. And then C is the net power in kilowatt. So in this case you need to multiply the number that we got from answer A by the mass flow rate here, okay, and the mass flow rate is given, so it is 5.807 kilogram per second, and the specific enthalpy unit is in kilojoule per kilogram, so you don't need to multiply it by the conversion number. So you will get the net power developed is 2046 kilowatt. Okay, and then the total rate energy that is added by the heat transfer. Here is the Q in over m dot time m dot. So you will get the Q in of 4622 kilowatt. The next topic is Ericsson cycle. From the previous slide, we know that the performance of a gas turbine power system can be improved by incorporating a regenerator and then reheater and intercooler. And usually the number of the compressor and expansion stage is limited by economic consideration. And in the real application, the number of the stage for the compressor and turbine is between 2 and 3 stages. And we can also make an analysis in case the number of the stage is unlimited. And if you look at on this TS diagram on the left side, we have several stage in the compressor side as well as in the turbine side. And you can see, for example, in the compressor side, at the entrance of the compressor 1, the stage is 0.1 here, and then there will be a compression inside the compressor 1, and then after the compressor exiting the compressor number 1, it will go into the intercooler, and the intercooler will bring the temperature back to the T1. So at this point, the temperature is equal to T1. Okay, and then it's entered the second compressor, temperature increases, and then the working fluid flow to the intercooler again, second intercooler, and it will bring the temperature back to the T1 here. Okay, and so on. So, and finally, at the exit of the last compressor, it is T2, and you can see in here that T2 equal to T1. And then on the turbine side, the entrance of the first turbine is state number 3, and then doing expansion, the temperature decreases, and then the reheater increase the temperature back again to T3 here, and then it's enter the second turbine, and then the second reheater bring the temperature back again to T3 here, and so on, so that at the exit of the last regenerator here, this is T4 here, the temperature is the same as T3. So in this case, each reheater bring the temperature back to the temperature at the entrance of the first turbine. Okay, and also we can see here that the regenerator enable the heat required to bring the state from 2 to 3 here is supplied by the heat rejected when the working fluid undergoes the process from state 4 to state 1 here. So with this condition, this means that the supply of heat transfer from external source is only used for the reheater here. This is the Q in from the external source. So when the number of the stage inside the compressor and inside the turbine is unlimited, so we have the process here that the heat is added when the temperature is TH, and then the heat is rejected when the temperature is TC. So the process that follow this rule, it's called Ericsson cycle. And as you can see in here, the Ericsson cycle is also an ideal cycle. Okay, and then the efficiency of this Ericsson cycle also follow the Carnot cycle efficiency formula, which is 1 minus Tc over Th. The next one is the Stirling cycle. So this is the PV and TS diagram for the Stirling cycle. This cycle consists of 4 reversible processes. The first process, it's called isothermal compression, that bring state 1 go to state 2, so isothermal. So it's mean T1 equal to T2. So you can see clearly in the TS diagram here that the process line connecting state 1 state 2 is a horizontal line here. And then the second process is the constant volume process. This change the state 2 to state 3, and then during this process Q in is added. Sorry. And then process number 3 is isothermal expansion from state number 3 to state number 4. So isothermal, so it's mean T3 equal to T4 here. And then the last process here is the heat rejection, that change state 4 back again to state 1. Okay, so here we have the heat rejection key out. Okay, so Stirling cycle is still an ongoing research area. So, and to my knowledge, I haven't seen any engine using Stirling cycle and it is in the market, but I know that there are several people are still doing a research and development for this Stirling cycle, and probably sometime in the future we will see this Stirling cycle to be applied to the one of the engine, and so that we will have more option, because right now we only have auto and diesel cycle. Okay, the next topic is gas turbine based combined cycles. The idea behind this combined cycle is the same as the combined cycle in the vapor power cycle topics. So the energy discharged by heat transfer from one cycle is used partly or wholly as the heat input for the other cycle. So we have the schematic here. On the top cycle, let's say we have a gas power system here. We have a compressor, and then we have a combustor here. So we have Q in entering the system, and then we have the turbine, and then at the exit of the turbine, it is step number 4. The gas temperature is still high, and the energy inside this working fluid is transferred to the other working fluid. So it is a bottom cycle inside the heat recovery steam generator here. So the bottom cycle is the vapor cycle. So we have a pump, and then heat recovery steam generator, and then we have vapor turbine here, and then condenser. So with this combined system, the Q in here is only in this side, okay, and then the net work is coming from the gas cycle side as well as from the vapor cycle side. So the overall thermal efficiency of this combined cycle will be the network from the gas cycle side plus the network from the vapor cycle side over Q in. So we will expect an increase of the thermal efficiency with this combined cycle. And then we can also apply an energy balance inside the heat recovery steam generator here. So the term on the left side here is from the vapor side, so m.v times 87 minus 86. This represents the heat received by the steam working fluid, equal to the energy discharged by the gas stream side here. So m.g times h4 minus h6. Okay, so once we have H7, H6, H4, and H5, we should be able to get the ratio of the m.v over m.g. Okay, let's take a look on this example. So this is the combined gas turbine and vapor power plant. A combined gas turbine vapor power plant has a net power output of 45 megawatt. Air enters the compressor of the gas turbine at 100 kilopascal, 300 Kelvin, and is compressed to 1200 kilopascal. The isentropic efficiency of the compressor is 84%, and then the condition at the inlet to the turbine is 1200 kilopascal, 1400 Kelvin. Okay, and then air expands through the turbine, which has an isentropic efficiency of 88%, okay, to a pressure of 100 kilopascal. Okay, so it's same as the pressure at the compressor entrance. The air then passes through the interconnecting heat recovery steam generator and is finally discharged at 400 Kelvin. Steam enters the turbine of the vapor power cycle at 8 megapascal, 400 degrees C, okay, and expand to the condenser pressure of 8 kilopascal. Water enters the pump as a saturated liquid at 8 kilopascal. The turbine and pump of the vapor cycle have isentropic efficiencies of 90 and 80% respectively. The first question is determine the mass flow rates of air and the steam, each in kilogram per second, and then the net power developed by the gas turbine and vapor power cycle, each in megawatt, and the thermal efficiency. And the second question is develop a full accounting of the net rate of exergy increase as the air passes through the gas turbine combustor. Okay, and the reference condition for the exergy analysis is T0 equal to 300 Kelvin and P0 equal to 100 kilopascal. Let's see the solution of this example. Left side is the schematic of the system. On the top system we have a gas power system consisting of compressor, combustor, and turbines, and you can see several number representing the given condition at, for example, state number 1, T1 is 300 Kelvin, and then P1 is 100 kilopascal, and then the compressor efficiency is given here 84%, and then at the entrance to the gas turbine, T3 is 1400 Kelvin, and then P3 is 1200 kilopascal. The turbine efficiency is 88%. Okay, and then in the vapor cycle, in the bottom cycle, state number 7, entrance to the turbine, temperature is 400 degrees C, pressure is 8 megapascal, and then the turbine efficiency is 90%. And then at state number 9, I believe this is entrance to the pump. It is assumed that state number 9 is at saturated liquid, pressure is 8 kilopascal, and then the pump efficiency is 80%. And then at state number 5, the temperature is given, so T5 is 400 Kelvin and P5 equal to P4, it is 100 kilopascal, and this is the assumption. So each component is analyzed as a control volume at steady state, and then the turbines, compressor, pumps, and interconnecting heat recovery steam generator operates adiabatically, and then we can ignore the impact of kinetic and potential energies, and then there are no pressure drops for flow through the combustor, heat recovery steam generator, and condenser. And then for the gas turbine cycle, the working fluid is air and can be modeled as an ideal gas, I believe. And then this is the reference condition to analyze exergy. Okay, once again, we don't need to determine step by step the properties at each state, because I believe that you should be able to do it. So in this example, the properties at each point is shown in the table. So starting from state number 1 through number 5, this is in the gas cycle side, and then state 6 to state number 9, so this is inside the vapor cycle side. So we have the enthalpy, and then we also have the S degree here. So once you get the properties at each state, then next step is you can determine the ratio of the vapor mass flow to the gas mass flow. So by applying an energy balance inside the heat recovery steam generator, so you will get that m dot v over m dot g is 0.1547. The next step is to calculate the network from each cycle here. So the first equation here is the network from the gas turbine side, and the second one is the network from the vapor cycle side. So we have m dot g as well as m dot h. So the value of the enthalpy has been shown in the previous slide, and then we have two variables here, mg, m dot g, m dot v, but we know the ratio between m dot v to the m dot g, so that we can just retain one variable here, which is m dot g, and then we replace m dot v by the ratio here. Okay, so then from the problem, the network is given. It is in megawatt, so 45 megawatt. So megawatt here equal to kilojoule per second. So in this case, it's mean that we need to calculate the mass flow rate. Okay, you need to calculate the mass flow rate. So by substituting the number here, so we should be able to get the mass flow rate of the air. It is 100.87 kilogram per second. And then knowing the ratio between m dot v to the m dot g, we should be able to get the m dot v here. So 15.6 kilogram per second. And then once we got the mass flow rate for each working fluid, then we can plug in the number to get the network in megawatt. Okay, so the network from the gas turbine side is 29.03 megawatt, and then from the vapor cycle side we get 15.97 megawatt. Okay, and then similarly we can calculate the Q in, and in this combined cycle the Q in is only used inside the combustor of the gas turbine side. Okay, and it is m dot g times h3 minus h2. Okay, so we have all number in the parameter, and we just need to plug in. We will get Q in of 85.3 megawatt. Then the efficiency is 52.8%. So it is, I believe, the highest efficiency so far compared to the previous problems. Okay, the next one is the exergy analysis. First is the net rate of exergy increase of the air passing through the combustor. We use equation 7.18. Okay, so you need to have a look what is the equation 7.18, and this is the exergy change for a control volume, and this is the formula. So once again, this is the net rate of exergy increase through the combustor. So it is m dot g times the change of the enthalpy minus T0 times the change of the entropy. Okay, and this is air and can be assumed as ideal gas. We can estimate the entropy change by using this formula. Okay. Okay, and then with assumption number 4, so it's mean there is no pressure drop inside the combustor, so it's mean P3 equal to P2, so it's also mean that this is a 0, so ln 1 here is 0. Okay, then we get the net rate of exergy increase through the combustor is 59.48 megawatt. And then the next one is the net rate exergy that is carried out of the plant by exhaust airstream at state 5 here. Okay, so this is the exergy difference between state 1, that's entering the system, and the exergy that leave the system at state 5. So here, so you can see there is the same formula, but now it's between state 5 and state 1. So the exergy, the rate of the exergy leaving the system, it is 1.39 megawatt. Okay, and then the next one is the net rate of exergy carried out of the plant as the water pass through the condenser. Okay, pass through the condenser. This means between state number 8 here and state number 9. And see in here the formula is the same, but now the working fluid is steam. So you can get S8 and S9 here from the corresponding steam table. So you will get this exergy rate of 1.41 megawatt. The next one is the rate of exergy destruction for air turbine, compressor, steam turbine, pump, and heat recovery system. In this case, we will use this formula because it is easier. So T0 times sigma dot here, and then sigma dot here is m dot g times delta S. This is for the air turbine, and same thing for the entropy change. We use this formula for the air working fluid, and then by plugging all number, you will get the rate of exergy destruction inside the air turbine of 3.42 megawatt. And then same thing here, this is the rate of the exergy destruction inside the compressor. Okay, and the next one here is the rate of the exergy destruction inside the steam turbine, and this the last one is inside the pump, 0.02 megawatt. And then, oh, not the last here, so we still have here the rate of the exergy destruction inside the heat recovery steam generator. So we have slightly different formula for the ED dot inside the heat recovery steam generator, because this is heat exchanger with two stream, and both stream do not mix. So review again chapter 7 about the exergy destruction for this kind of the system. So you will need to use this formula. So T0 times m dot g times delta S from the gas side plus m dot v times delta S from the steam side, and just plug in all the number here. You will get 3.68 megawatt. And this is the summary of the exergy analysis. So on the first column here, it's just showing the name of the item. So the net exergy increase of the gas passing through the compressor to the combustor. So here we have 59.48. So this means this is 100% exergy that coming into the system, and this is what we pay. Okay. And then the next one is the net power developed by the gas turbine and then by the vapor cycle. So this is directly the network there. And then next one is the net exergy loss, okay, with exhaust gas at state number 5. And then this one is from water passing through the condenser. And the next one here is the exergy destruction inside different component here, air turbine, compressor, steam turbine, and so on. And this is the value in percent. Okay, and 70% here I believe is estimation based on the fuel and fuel exergy. Yeah, if you remember in chapter 7 that of the 100 exergy entering the system, some of the exergy is destroyed due to irreversibility inside the combustor itself that cannot be analyzed in this chapter, and also flowing out of the system through the stack. Okay, and they were assumed about 30%. So 70% stay inside the combustor, and it's used for this gas turbine cycle. So in case we only have 70% of the exergy, this is the new percentage of the exergy analysis.